What's the answer? Are you hearing me? Hello? Alright, so it seems that Mr. Moss sent a message in the chat. Right, so let me go over that again. We are continuing from where we left off a while ago, right? We had um 0.054 times 1400, we got 226. We got 22.0 minus 17.5, and we have 4.5. Now we're trying to figure out what's happening at the top. 226.8 times 4.5. What's the answer here? All right. So we see 1020, right? Okay, that's good. 1020.6. All right, thank you, Mr. Hakim. All right, you guys need to type faster, okay? Type much faster. You guys are typing slow. All right. So negative here, 0.1, 0.104 times 78 times negative 78. What do we get? What we get? What we get? What are we getting here? 0.104 times 78 times negative 78. All right, so remember the negative, right? So we'd have about negative, right? Thank you, Mr. Moss. Right, 0. So we'd have 8.1112. No, the final thing, right? Let's do this. 1020 divided by 6 divided by 8. Sorry, 8.112. What are we getting there? 1020.6 divided by 8.112. What do we have there? All right, 125.7. All right, DeMarco, you want to check that again? Right, 1020.6 divided by 8.11. Probably is my writing here. Let me fix that. All right, so somebody said 125.7. I'm getting 125.8. That's what I have. Right, it's the same thing. Not too far off. So we just use 125.7. All right, 125.7. All right, 125.7, 125.8. Right, so this is our specific heat capacity of our metal, right? This is the specific heat capacity of our metal, Cm. And I know you probably won't remember the units, right? But it is joules per kilogram per Kelvin or per degree Celsius, right? Um, I hope over time you would get more familiar with the units. All right, but for now, I'll help you out because of time. So we'll use this to find the approximate value for our um for our for our
Metal.
yeah, for our metal. We'll find the type of metal. Now we did our calculation in kilogram, but obviously here they did theirs in grams. Right? They did theirs in grams. I'm just realizing that I will Let's see how I can do this. Let me see if I can find a scale in grams quickly. It should take no longer than 1 second. Just realizing that they did yours in kilograms. You should not do yours in grams because you might get it wrong for CSEC. Right? We don't want to give away any points. We want to ensure that we do all the conversions, necessary conversions, to ensure that we get the right mark. If they say you can do it in grams, you can go ahead and do it in grams, right? But if they don't specify, do it in kilograms. We're not giving away any marks, right? Specific heat capacity of metals chart in joules per kilogram per degree Celsius. Let's see if we find something on this. All right. Okay, that's something. There's something here. Oh, but this table has two. Let me use this one. Yeah, this is good. This is good. Come on. It's a screenshot. Specific heat capacity. Right. Next up. Change this. Good. Here that is. And put this here. Perfect. Yeah, so as I was saying, try and do all your calculations or most of your calculations in kilograms, convert to the SI unit because we don't want to give away any marks. You don't want to give CSEC any marks. All right. You want all of them. Question? All right. So our specific capacity is 125 joules per kilogram per Kelvin. All right. This is our final specific heat capacity of the metal. Now we'll try and find which one is the metal. Which one is the closest one to 125?
Gold.
Right. What a thing. We are using gold that we didn't know. Right. We're using gold and we didn't know. So our specific capacity is close to gold. 125, 129. Right. So that's our metal. So are we clear on this calculation? Right?
Yes, sir.
All right, so Akeem is good. I know that Devontae is also good. Anyone else, please let me know. Please stop me. All right. Let me know if you're not understanding. Don't do me like what the grade nines do me. They wait until I give them an activity that says, I don't understand that you did in the class. I'm like, wow. All right, are we clear? All right. I will take that as a yes. Remember, you can always go over as revision. So we'll move on now to specific latent heat. So let me get that slide up. So we'll do a lab similar to this. So we obviously will have the metal, we know what type of metal it is, right?
Yes, sir.
Let me get the slide up. So move on now. For the last 5 minutes, we'll just introduce you to specific latent heat. So this is what we want to accomplish this week. Nice. Okay, good. Save and share. All right, so let me know if you're seeing this. All right.
I'm seeing it, sir.
All right, good. So specific latent heat, we want to demonstrate that temperature remains constant during a phase change. We're going to apply the relationship EH equal ML, and what we say EH is again?
Heat energy.
Right, so EH is our heat energy and mass and then latent heat. We're going to determine the specific latent heat of vaporization and fusion of water. This is a particular lab that we're going to do. We're going to distinguish between evaporation and boiling using the kinetic theory, all right, to explain both of them. Now, heat energy. All right, so we're going to talk about this for the last 5 minutes. So the heat observed or heated release or the heat released at constant temperature during a change of phase is known as latent heat, right? So whatever heat is absorbed by the material during a phase change, when changing from a solid to a liquid or a liquid to a gas, right? We call that heat latent heat. Now, what is the freezing point of water? At what temperature does water freeze?
What's that?
0 degrees.
Exactly, 0 degrees. Water freezes at 0 degrees. And at what temperature does um water boils or water?
100 degrees, sir.
Exactly. So water boils at 100 degrees and it freezes at 0 degrees. So this transfer of heat does not cause a change in kinetic energy of the molecules, right? During latent heat, there's not a change in kinetic energy of the molecules. It's just heat energy applied to the system so that there's a phase of change. So there are four main changes of phases, right? We have melting. Melting is what? Just say,
When it's solid, that turn into liquid, sir.
all right, so solid to liquid. Boiling is what?
Um, Probably liquid to gas.
Liquid to gas, right? Condensation is what?
Um, Liquid to solid. I
Let's try
think.
that again. Condensation, right?
Compressing.
Think about think about your freezer, right? Or think about let's say, think about when you're in the car, right? And you see condensation on the window. What is happening there?
Like fog.
I want solid to liquid, liquid to gas, gas to solid, gas to liquid. Which one is it? Get
Oh,
condensation.
I feel.
Just liquid.
Right, so gas
Yeah,
to liquid.
gas.
Exactly. And solidification is what?
Liquid to gas.
All right. Liquid to gas. Let's try that again. Liquid to
Oh,
solidification.
liquid to solid, sir. Sorry.
All right. So liquid to solid. All right. So let's go. So liquid to solid solidification. Freezing happens here, right? Freezing. All right. Just to give you a better understanding. So there are two types of latent heat. For the last 2 minutes, right? You have heat of fusion and you have heat of vaporization. Now, the heat of fusion. So let me start you out. Let me help you out. So the heat of fusion is the heat required to change from what? Fusion. Think about it.
Uh, Two matter, sir.
Go again.
Two matter.
All right. Let's no solid to liquid. That's what we're working with. All right. So heat of fusion is the amount of heat required to change a solid into a liquid, right? You're applying heat and it begins to melt. So that's heat of fusion. While heat of vaporization is used to change a liquid to a gas. So vaporization, vapor, right? And this happens through boiling. Now I put it to you that the heat of fusion when going from a solid to a liquid is the same heat of fusion when going from a liquid to a solid. And I also put it to you that when the heat of vaporization, right, is the same amount of heat when going from a liquid to a gas, is the same amount of heat going from a gas to a liquid. Is either the heat is released or the heat is gained by the material. So when going from a liquid to a gas, heat would be absorbed by the material, and when going from a gas to a liquid, heat would be released from the material into the atmosphere or to its surroundings. All right.
Just like your water cycle.
No, you could say that, right? You could say something like that, right? So if we have a water, if we have a a cup of water, right? And we apply heat. I will do this in the next class, right? I apply heat, right? Heat will be absorbed by the fluid, and then it will turn to gas. We'll do this next class. We'll go over it again tomorrow. But when releasing heat, right? When heat is going out of this container, you would find that the particles will lose energy, right? And then they will come together and form a solid. We'll go through it again tomorrow, right? But we just wanted to start today. Um, all the best, everyone. I am still in the process of marking the labs. I think I'm at lab 6, so I have 2 more labs. I mark them. I mark all the lab 1s, all the lab 2s, all the lab 3s. You want from the time now. You have free time now. Work on the labs, right? If you remember where you need to catch up on, I'm seeing a lot of persons giving away marks, a lot of marks, right? I haven't seen somebody getting 9 out of 10. All right, for the first lab, I saw persons getting 6, 4, 4, 3, 2, 1. Look on your mark scheme. When you get back your labs, look on the mark scheme. Look what is required of you. For me, right, for you to get marks, for me, you need to have sources of error, limitation, precaution, conclusion. These are some basic things that you need to have, right? And for some of the labs, they will have observations. You should ensure that you place these inside the labs. You're giving away too much marks. All right, but we'll talk about this. Hopefully, we get to finish this lesson for this week and we can talk about it more by Wednesday or so. All right, so all the best, everyone. Enjoy the rest of the day.
All right, sir.
All right.